For the epsilon delta proof of a limit, I think it's very important that we start first of all with an understanding of what epsilon and delta are and how we're using them to prove that a limit exists. I've got here just a graph of any linear function of a straight line f of x. And the green point is the value here where I'm showing the limiting value for this particular function when x equals a. So this is your x-axis, this is your y-axis. So all the values along the x-axis are along the horizontal axis. All your values along the y-axis are really f of x, right? So f of x and y are kind of used interchangeably. And L is just a specific y value of this function at a certain value of x. So in this case, we're saying that when x equals a, the function is equal to L, the limit, okay? So when x equals a, the function f of x is equal to L. So that could be a real value, like I'm showing here where I've got a solid line and it's an actual value at L. It could also be that the function is just not defined at that value, and then we would have sort of a hole in the graph there, but it's still a limiting value. This would still be L. And so that would be what the function is sort of tending towards at that particular value of a, all right? And that's all a limit is. And so when we are trying to use the epsilon delta definition of the limit, then what we're really saying is that we're choosing some value here that we're going to call epsilon. So really what we're doing is just taking the limit and adding just a little bit onto it, or we can go the other way and we could subtract epsilon from L as well. So we're either going to be above or below, and those should be the same distance from L here and here, okay? It's the same value. What we're saying is we want to get as close to L as we can. It's kind of like some of you have been reading the examples of if you're doing a half of a half of a half of a half, you're never actually going to get to the end because you can always still take a half of a half of a half of a half, but you can see where you're going to end up if you could. And that's the idea with a limit. So what we're going to do here is just make these values of epsilon closer and closer and closer to L. And what we're asking is, if that limit exists, is there a value of x that would correspond to that in the function? In other words, can we find an x value along this x-axis where we would always be able to get that value of the limit minus epsilon, like really close to the limit, but not exactly on it? And so that's where we use the delta idea. And so the delta is actually an x value, and the epsilon is actually a y value, sort of like the epsilon is L plus the y value is L plus epsilon or L minus epsilon. So f of x is either L plus epsilon or L minus epsilon. So the y value we want is really close to L, but not exactly on it. And the x value that we're using is actually being changed by delta. And so the x value is either a minus delta or a plus delta. And that's our x value that we're going to talk about. And so when we're doing this definition, when we're trying to prove that this is a limit, what we're really trying to say is that I can get closer and closer and closer to this L value. And as long as I'm getting closer and closer, for any value I pick, I should always be able to find the X value that corresponds to it if it really exists. And that makes sense, right? I can't get a Y value from my function unless there's an X value that makes that happen. Y is always a function of X. In other words, we have to have an X value to put into our equation to give us that value of Y. So that's why we write it like this. We always talk about X minus A, absolute value, always being less than delta, because that's a value along the x-axis. And then when we're talking about epsilon, we talk about the function f of x minus the limit always being less than epsilon, because that's a value along the y-axis. And so any epsilon value is y minus the limit, or y plus the limit. We're always working from L and adding onto it or subtracting from it to get that epsilon value that gets us really, really close to L, but not exactly on it. So we have these two equations, and the idea for this assignment is just to show that the two equations, that you can make the delta and the epsilon sort of represent each other. And as soon as you've done that, as soon as you can find a delta and write it in terms of epsilon, you've shown that for any x value that we choose, that there's a corresponding y value getting closer and closer to the limit. So here's an example. Actually, I think the video is getting kind of long. I'm going to make a second video that shows you an example of how we would use this definition to prove that a limit exists.